Oh yeah, thermal physics isn't that hard. I mean, how hard could it be? It's not rocket science. Or is it? Sorry about that. I was talking to my good friend. You might have heard of him. His name's Elon Musk. And he was just telling me how he plans to go to Mars by 2029. But I reckon we can get there a little bit sooner.
Let us consider the launching process of a water bottle rocket. A water bottle rocket is operated by partially filling an empty bottle with water and attaching the bottle to a launcher system. Using a pump in the launcher system, the pressure of the remaining air in the bottle is increased and its temperature increases too, by the ideal gas law. The rocket has a fixed volume. As we compress the air inside, we increase the pressure of the gas molecules inside the bottles. As the pressure increases, the potential energy inside the bottle increases. This causes the water inside the rocket to push down against the cork. Once the catch of the launcher is released, the bottle leaves the cork. Immediately after this point, the water rushes through the nozzle and creates a thrust in the opposite direction, countering the weight force and air resistance. This is due to the expansion of the high-energy compressed gas inside the bottle. A good rocket design will maximize the amount of potential energy converted to kinetic energy. During this process, the pressure of air begins to fall and the temperature of the air in the rocket decreases. After all the water is expelled, the cooled air in the rocket finds it easy to leave, so the pressurized air is expelled, giving the rocket a final boost. Since the mass of the rocket is far less now than at launch, even a small expulsion of air can considerably propel the rocket. This completes the burnout phase, and the rocket enters the ballistic stage, where it is only affected by gravity and the drag force. In practice, however, due to the aerodynamics of the rocket, this drag force may be in a different direction, causing the rocket to fall at an angle and lose stability. The first stage of this process was the construction of a water bottle rocket and water bottle rocket launcher that could release the rocket at a given pressure. A cork and catch style launcher was chosen. However, many challenges arose during its construction. The catch mechanism that stopped the water bottle rocket from being released at high pressures was incredibly difficult to make. The cork had to be held steadily in place, and the pegs that aligned over the water bottle rocket's nozzle had to be precisely aligned so that the water bottle rocket didn't leave before it was supposed to. Additionally, the bottle had to be held upright using the walls of the launcher. However, this added an unaccounted for friction force, which significantly impacted our results, as you'll later see. Additionally, since the rocket was designed after the launcher, the initial azimuthal angle between the fins of the rocket of 60 degrees was unable to fit inside the constructed launcher. Consequently, a different spacing angle was used. However, this affected the flight of the rocket. In this experiment, we compared theoretical predictions to the empirical filling percentage that maximized height achieved with the rocket. We will now derive the maximum filling percentage. I highly encourage you to pause and read through this, especially if you're marking this and not just watching for fun on YouTube. Since the pressurized gas in the rocket expands very rapidly, approximately 0.22 seconds, we can consider it adiabatic. Thus, we know PV to the gamma is a constant, K. We find the work done by integrating the pressure between the initial and final volumes and find it to be K over 1 over gamma multiplied by the final volume to the 1 minus gamma minus the initial volume to the 1 minus gamma. Now, if we let x be the percentage of the bottle filled with water, we have that V initial equals 1 minus xV, where V is the volume of the bottle. We can use this to find that K equals P multiplied by 1 minus x to the gamma times V to the gamma. Substituting this into our initial equation for work yields the following expression. We note that for a fixed initial volume and pressure, we can maximize this using calculus to find the filling percentage which maximizes work done by the gas. This yields a filling percentage of 56.88%. This, however, does not help us to maximize the height achieved, as the max height and work done are related by equating potential energy to the work at the max height. Thus, the max height is proportional to the ratio of the work done to the mass of the rocket, as shown. The mass of the rocket is not constant throughout the flight due to the obvious expulsion of water. However, initially, it is a good approximation to take the mass during launch to be constant, as the initial mass of the water is released very quickly. Thus, the gas does work to launch the initial mass of water into the air, and to maximize this launch work, and thus the total height, we can maximize the ratio of work to initial mass.
The mass of the rocket is the sum of the empty bottle mass and water mass, which can be found using its density. Dividing our previous equation by work by this mass yields the following expression. We solved this for a maximum using numerical methods, giving us the following plot of work per unit initial mass and filling percentage. We thus see that with a 1.25 liter bottle and launching at 20 psi, the max height achieved is optimized by taking a filling percentage of 25.12%.
So Jerry, how did you calculate the maximum height of the rocket? Well, I'm glad you asked. We used two methods to calculate the maximum height of the rocket. We utilized the time to apogee, the maximum height, using the Blaze software created by fellow classmate Vijay and Dan Wheeler. The second method was to use a high-resolution camera to record the launch and create an artificial scale to measure the height. Both methods involved recording the experiment.
The second method was attempted, however, it led to many inconsistent results, as although every effort was taken to level the camera and create a good reference scale, the flight path of the rocket was not perfectly vertical, hence there was a large amount of parallax error in the analysis. Consequently, the Blaze method was used.
Now, let's head into the lab for some analysis. As seen, the water bottles were filled in 20% filling increments, and the maximum height achieved was using a 40% filling percentage. Now, this is significantly higher than the 25.12% theoretical maximum propounded by the model. This difference can be attributed to the limitations of the launcher.
You see, since the cork had to be attached to the launcher, there is a hole through the cork where some water can leak. As we increase the pressure, more and more water begins to leak through the hole. To mitigate this effect, a low pressure of 20 psi was used. Additionally, the two wooden walls of the holder act as a holster for the rocket before launch. These are continually in contact with the rocket until it leaves the launcher. The theoretical model doesn't account for this friction force, consequently predicting that the rocket should go higher than it actually does. But here's the real kicker. Slow motion analysis of the launch shows that while the rocket is in the friction zone, where it is leaving the cork but still between the wooden walls of the launcher, a significant amount of water is lost. Consequently, by the time that the water bottle leaves the launcher and is allowed to expand freely, the initial filling percentage has changed. This theory is consistent with both the theoretical and empirical results.
The highest launch was achieved with a 40% filling factor. By the time the rocket had left the friction zone, the actual filling factor is likely to have been near 25%, agreeing with our model. It is also seen that the shape and functional relationship of the empirical results closely resembles a theoretical model, with a 20% linear shift. This means that during the friction zone, approximately 20% or 250 milliliters of water is being released. In future designs, this effect can be mitigated by increasing the spacing between walls or using stilts to ensure that the rocket's path stays upright.
Whoa! Looks like we made it to Mars before Elon Musk. Thank you guys for watching. I hope you guys enjoyed. Make sure to like and subscribe and stay tuned for more insane content.